quantum computing. And
And yeah,
yeah,
I
I
put
put
another
another
timeline
uh,
which I
which I
uh, was
was
talking last
talking
year,
last year,
uh,
uh,
and then I
and then
wanted to
I
stop
wanted to
talking
stop
about it
talking
again,
about
but
it again, but
considering the world
considering the world
situation these
situation
days,
these days,
I want to
I
mention
want
that
to mention that
last year was the
last year was
80th
the 80th
year after the
year
end of
after
the
the
World
end of
War
the
II,
World War
and
II, and
we don't want to
we don't
repeat
want
the
to repeat
history.
the
And
history. And
unfortunately, quantum
unfortunately,
mechanics
quantum mechanics
apply
apply
to
to
atomic
atomic
bomb,
bombs,
and I
I
think
think
our
our
quantum
new
technology
quantum
should not be
technology should
applied
not
to
be
any
applied to any
weapons or
weapons or
killing
killing
people,
people, and
and should be
should
applied
be
for
applied for
our
our
happy.
happy.
Okay.
Okay,
So,
so
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 actually,
actually
our field
our
was
field
not
was not
really
really
started
started
uh,
uh,
for
for
quantum
quantum
computing,
computing,
and
and
our research
our
was more initially
research was
motivated by
initially
more
motivated
fundamental
by
quantum
more
mechanics.
fundamental quantum
So,
mechanics.
as you know,
So, as you know,
the question
the question
about the
about
superposition
the
in macroscopic
superposition in
object
macroscopic
is
object
a
is
big
a big
question from the beginning of
question
quantum
from the
mechanics.
beginning of
Even
quantum mechanics.
Erwin
Even
Schrödinger
Erwin Schrödinger
questioned why we
questioned
don't see any
why we don't see
superposition in
any
our
superposition in
daily
our
life.
daily life.
And in
And in
1980, Tony
1980,
Leggett
Tony
uh,
Leggett uh,
came up with
came
an
up with an
term, quantum
macroscopic quantum
coherence,
coherence, and then
he
uh,
proposed
proposed
a system
a
in
system
which
in
we may
which we
see
may see
quantum
quantum
superposition in a
superposition in the
macroscopic scale.
macroscopic scale.
That was
That was
really
really a
superconducting circuit.
superconducting
So
circuit. So he
he
proposed
to see
to see
superposition of
superposition of the magnetic
magnetic flux
quantum
inside
inside the
trapped in a
trapped in a
superconducting
superconducting
loop,
loop,
one
one
extra
extra
flux
flux
quantum
quantum
in or
in or
out
out
of the
of
loop,
the loop,
and then
and then
create a
create a
superposition
superposition
between
between those
those two
two
states.
states.
Here
Here
in this
in this
superconducting ring,
superconducting
there
ring,
are
there are
millions of billions or
millions of
trillions
billions or
of
trillions
electrons
of
or Cooper
electrons or
pairs
Cooper pairs
circulating around,
circulating
and
around, and
the direction of the
the
current
direction of the
changes
current changes
when
when
magnetic flux,
magnetic
single
flux,
flux
single
quantum
flux
tunnels in
quantum
and out.
tunnels in and out.
So it's kind
So
of
it's kind of
creating
creating
superposition between
superposition between
clockwise and
clockwise and
anti-clockwise
anti-clockwise in
circulating
circulating
persistent
persistent
currents
currents
in the loop.
in the loop.
Okay,
Okay,
triggered by
triggered
this
by this
proposal.
proposal.
uh,
Okay,
before
before
that,
that,
I
I
also
also
mentioned
mentioned
that
that
here,
here this
this effective
effective
energy potential in
potential in
double
the double shape is created by the sum of this inductive energy in the loop, inductive energy in the loop, and also the Josephson energy from this weak link of superconducting tunnel junction. And so the Josephson energy was proposed by Josephson effect was proposed by
Brian
Brian
Josephson in
Joseph
1962 when he
in
was a
62 when
master
he was a
student of
master
Cambridge
student of
University.
Cambridge University.
And
And
so
so
what he
what he
predicted
predicted
was
was
that
that
group appears
group
can
pairs can
freely
really
tunnel across the
across the
Josephson
Josephson
junction
junction
between two
between two
superconducting
superconducting
electrodes.
electrodes.
And
And
so this is a
so this is the description
description of Josephson
description of
effect in
Josephson
the
effect in the
charge number
charge
basis.
number
So n
basis.
is
So
the
n
label
is
of
the
the
label of number of Cooper pairs tunnels across the
barrier
barrier
from
from
left
left
to
to
right.
right.
And then
And then uh, basically
the Cooper pairs
the
tunnels
Cooper pairs
from
tunnels
the
from
ground
the
state of the
ground
one
state of the one
superconductors to the other ground
superconductor
state
to
of
the other
the
ground state of
other side of the
the other side
superconductor. So
superconductor. So
uh, independent of the number
independent
of
of
the
the number of the
tunneled Cooper pairs,
tunnel Cooper pairs, all the
energies of the whole
energies of
system
the whole system
doesn't
doesn't
change. So
change. So
basically, all the
basically, all the
states with
state
different
with different
Cooper
number
pairs
of Cooper
tunnel
pairs tunnels
or degenerate,
or
and
degenerate,
the
and
neighboring
the
states are
neighboring states
basically
are basically
coupled by the
coupled by the
tunneling of single
tunneling
Cooper
of
pair.
single
So this
Cooper
is
pair. So this is
nothing but the
nothing but
one-dimensional
the
type binary
one-dimensional
model
type
in
binary
a
model
charge
in a
number
charge
basis.
number
It's
basis.
similar to
It's a
one-dimensional crystal
dimensional
lattice.
crystal lattice.
And so
And
the
so
Hamiltonian
the Hamiltonian
is written like
is
this,
written like this, and then
the
the
Hawking energy in this
Hawking
case is
energy in this
basically the
case is
Josephson
basically the
energy.
Josephson energy.
And
and in the conjugate variable of phase conjugate to the number of the Cooper pairs, we obtain this Bloch band or cosine band in phase space. So, so this cosine band actually creates this double wave potential proposed by Tony Legge. Okay, so triggered by Tony's proposal, many people started uh, uh, working on this to see the quantum coherence in the macroscopic scale. So actually, as Bupen told us, the Nobel laureate last year worked on this physics in 1980 to see macroscopic quantum tunneling. Okay, they haven't they didn't succeed to see the coherence yet, but they demonstrated macroscopic quantum in 1980, in the middle of 1980s. So actually, yeah, uh, this is a picture from their Nobel lectures, and they also signed in the famous chair at the Nobel Museum. Okay. So and so in 80s they succeed to see macroscopic quantum tunneling. That means uh, when they tilt this double wave potential by applying, in this case they use the current bias Josephson junction and tilt the cosine potential, and in each wave of the cosine potential, basically the state of the whole circuit is quantized. And then they succeed to see the effect of the quantum tunneling across this potential barrier and as a saturating tunneling rate at low temperature. So that was an evidence of the quantum tunneling in the macroscopic system, or actually this phenomenon is described by like a current and voltage in the circuit, not as like a position of single electron. So uh, this electrical circuit behaves kind of as a macroscopic quantum object. And then they also demonstrated that these energy levels are quantized inside this potential wave. So this is again not the energy levels of single electrons or single Cooper pairs. This is a quantized energy levels of collective motion of electrons in the circuit. So in 1980s, they observed this quantization by using microwave spectroscopy. Okay. So, and then in 90s, they looked at this quantization and dynamics in the basically the phase space. But in 80s, thanks to the uh, progress in the semiconductor industry and nanofabrication, people started to fabricate devices much less than micrometer scale. So, for example, Costa Rica proposed the uh, so-called orthodox theory of charging, single electron charging effect because of the smallness of the electrode. For example, here, this is a device I made in 90s. So like this tiny aluminum island in the scale of tens of nanometers, even a single electron charging creates a lot of charging energy because the capacitance is so small and the charging energy for a single electron is so large. So this charging effect dominates the handling transport of electrons in a device. And so so this is say new development in 90s. So and then because okay, this was in the normal state, but no superconductivity, and but when aluminum electrodes become superconducting below 1 Kelvin, we started to see this effect of single Cooper pair tunneling across Josephson junction. And here, the competition between the Josephson effect, which tries to delocalize Cooper pairs, and the charging effect, which tries to localize Cooper pairs, and gives interesting situation where we see the quantum fluctuation of the charge and the numbers and the phase compete. So here, the device called Cooper pair box, tiny aluminum island connected to the reservoir with the Josephson junction. At most one Cooper pair can tunnel in and out because of the large charging energy. So now you remember that in a large scale Josephson effect, all the charge number states are degenerate because we neglected the charging energy. Here, because of the charging effect, now the different charge number states has different energy due to the Coulomb energy, like a quadratic form. So if you choose the parameter correct and then apply the gate voltage bias to adjust the origin of this parabola, we can create a situation where only two charge number states nearly degenerate. So here, for example, in the Michel Deborah's group and Daniel Esteve in Saclay in France, they looked at this device and then looked at the behavior of the ground state and to see the expected charge number state in this device as a function of the gate voltage, showing this discretized step. So as you see the gate voltage, Cooper pairs are introduced one by one into the island. But if you look carefully at this step, so if there's no coherent superposition, this step is expected to be infinitely sharp, vertical. But because of this superposition effect between these two states at the step, there's always some finite slope for rounding because of the superposition. So that's what they demonstrated as a function of temperature. At low temperature, obviously, in the case of superconducting state, this slope fluctuates in contrast to the normal state case. So this is one evidence of the superposition happening between the two charge number states, low temperature state. And at NEC in Japan, our team worked on the similar device, but using spectroscopy to study the not only the ground state, but also the excited state. So here, again, in a similar device, we create a superposition. And then because of the superposition, now we have a bonding and anti-bonding state between the two charge number states that we observe in the microwave spectroscopy to see this opening of the anti-crossing of these two states function of the gate voltage. So this is kind of the evidence of the macroscopic quantum coherence between two different charge number states in electrical circuit. Okay, so then after doing, to be honest, when we did this experiment, we were not really aware of quantum computing or quantum bits. So we were just curious to demonstrate macroscopic scale quantum coherence. And then, but then around the time, people started talking about quantum computing and quantum bits. So we found it interesting and maybe we can use this device. So that brought us to the next experiment published in '99 to show the quantum coherent oscillation in this kind of device. So this is again similar Cooper pair box with a small aluminum island connected to the reservoir electrode and through a Josephson junctions. This is just a discrete Josephson junction. And so, and then by applying a very fast, 100 picosecond scale voltage pulse to control the chemical potential of this island, we dynamically change the relative energy between the 0 state and 1 state, and then use the coherent oscillations when we suddenly make them degenerate and they started oscillate in between. And then after the pulse, it was kind of frozen. So that's what we saw in this device as a function of time. And then you see clear oscillations between these two states. So we demonstrated it as a say kind of first demonstration of superconducting qubit or solid state. And so this is an artificial two-level system created in electrical circuit and coherent control macroscopic system. And later in TU Delft in the Netherlands, in Hans Muid team, we also demonstrated flux qubit. So here, in the superconducting ring, magnetic flux quantum tunnels in and out, and then we see Rabi oscillations induced by, in this case, microwave pulse manipulate this quantum bit. Okay, so yeah, probably most of you are familiar with this, but so in terms of electrical circuit language, our superconducting qubit is nothing but a nonlinear resonator. So usually in electrical circuit, we create LC resonator for oscillating circuit. And in the quantum mechanical picture, this LC resonator is nothing but a harmonic oscillator with equidistant quantum levels, quantized levels. But in our superconducting qubits, we want to have effective two-level systems. And for that, we introduce a bit of nonlinearity through this Josephson junction. As I mentioned, Josephson effect gives a cosine potential, which is harmonic and nonlinear. So by replacing inductance with a nonlinear inductance of Josephson junction, we distort the potential and then make these energy levels non-equidistant. And then we can safely derive the Rabi oscillation between 0 and 1 state, and to use these two levels as the basis of qubits. And we often call this system as an artificial atom, and because of that analogy with the natural atom, where the Coulomb potential of positively charged nucleus create the ions, and the levels for electrons are highly harmonic, and we can also use these levels for qubits. But of course, the size of the systems are largely different. Atoms are in angstrom scales. Our circuits are millimeter scale, and natural energy levels are also largely different. Atoms are in electron volts, and our circuits are micro electron volts or gigahertz frequencies. Okay, so any different. So these are all human designed electrical circuits. So we can choose any parameters we want. So we have a lot of freedom, and we can choose different topologies. And so other different qubits are also proposed and used. And so, yeah, we have a lot of freedom to design this thing. Okay, and again, I want to mention that these quantized in our circuits are not for single microscopic particles. It's a quantization of the collective motion of electrons or Cooper pairs in the circuit all together, oscillating back and forth. Okay, so and later in this field, there's another breakthrough idea, which is called circuit QED, circuit quantum electrodynamics. This is in analogy with cavity QED, which was developed in AMO physics in 1980s, coupling a single atom trapped in an optical cavity, and then the two-level atom can coherently interact with photons confined in the cavity when the coupling strength is large enough, larger than other dissipative rates, and that can also be implemented in our superconducting circuits, where our artificial atom is coupled to a microwave resonator on chip, which is also created by just superconducting circuit. And then here we can basically do this happy QED in the microwave domain. And later, we also developed an idea of waveguide QED, where even without the cavity to confine photons, our artificial atom strongly coupled to one-dimensional waveguide, again made of superconducting circuit. We can still study coherent interaction between the artificial atom and the propagating photons along the waveguide. If the spontaneous emission decay rate of this atomic excitation into the waveguide mode is much larger than the decay rate into other modes or dephasing rate. So here we can use this system as an interface between our qubit and the flying qubit along the optical or microwave waveguide. So from this development, the field of microwave quantum optics started. And later on, for example, an interesting idea of giant atoms were developed, where this artificial atom is not necessary to be smaller than the wavelengths of the microwave we use. So this artificial atom could be even larger than the wavelengths, and then some interesting things happen. All right, so so far so good, but then we had the big challenge against coherence. So our artificial atoms or our superconducting qubits are not floating in a vacuum, isolated well from the environment. Our circuits are sitting on the substrate up to many other degrees of freedom, like photons in the vacuum, photons in the substrate, and other environmental modes in the circuit. And our qubits also coupled to many different microscopic objects like charge defects, spins, and trapped vortices and quasar particles in the electrodes. So we have to fight against all those enemies in the environment. So initially, when we did this, started this experiment in '99, the coherence time was around nanosecond, and at least I was very pessimistic about the future. But thanks to the effort in the field worldwide, currently the best superconducting qubits has coherence time of around milliseconds. So there was 6 orders of magnitude improvement in the last 25 years. So because of that, these days, many groups in the world are developing large scale, or not yet fully large scale, but small scale superconducting quantum computers with tens or hundreds of qubits. So yeah, last year, Google reported the first demonstration of logical error suppression with surface code, quantum error correction code, and showing that if you use tens of qubits, 3 by 3 or 5 by 5 or 7 by 7 qubits, physical qubits, they can reduce the logical error per error protection cycle down to around 10 to the minus 3 level. Okay, this is still not enough for doing large-scale quantum computing. We want to achieve something like 10 to the minus 10 or 10 to the minus 15. So it's still a long way to go, but at least there's a trend to reduce this error. And to make it further progress, we have to increase we can increase the size of the code in a 2D array or qubits, but then it requires a lot of overhead. We need more qubits, more error correction steps. But also, if we could reduce the error rate of each operation, so like a single qubit gate or 2 qubit gate or measurement of each qubit, further down, this can also be dropped dramatically. So that's why we are currently focusing on improving these gates. So here in this Google experiment, single qubit gate is like 3.9 or better fidelity, and 2-qubit gates is 99.5 or something. But and measurement fidelity is about 99% or so. So still we need to improve those numbers. And yeah, for example, yeah, there are many other groups working on that. This is an example from Chinese group at Zhejiang University, and they implemented even more complicated quantum error correction code. And yeah, it's not yet break even or better error rate suppression yet, but at least they demonstrated this operation. So yeah, many other groups are now making progress. So so the challenges for our field is in two directions basically. So one is in the direction of higher fidelity, and the other is for larger system. Of course, we need many qubits to run large-scale quantum computers. So for superconducting qubits, it's now we are around here, like nearly 3.9 fidelity and about 100 qubit system. And our target, say, future large-scale quantum computing, is still a moving target, and theorists are working hard to reduce the overhead and requirement with a better error correction code, better architecture for fault-tolerant quantum computing, better algorithm, better applications. And so hopefully this target will come down to us, but not still, I have to say, it's still very far target. And but so we want to move toward that target. And in terms of scaling up, we have challenges like uniformity of the circuit and connectivity between qubits and wiring and heat load if you have more qubits, and scaling of the classical part of control electronics, which can consume a lot of space and a lot of energy. And yeah, probably we have to move to multi-chip architecture, modular architecture, and even multiple bridges in future. And that's our challenge. And it was the higher fidelity operations. We have to fight against decoherence, especially very nasty two-level systems that are unknown environmental degrees of freedom, probably due to the defects at the surface or interface of the devices. And we have to well summarize the qubits, suppress external noise, crosstalk, and control error, and also residual coupling between neighboring qubits. And we also need to reduce readout back action. So those are our challenges. So, okay, 25 years ago, I never imagined that we can reach 90% fidelity. 10 years ago, I never imagined that we could reach 99. And nowadays, we are almost reaching 99.9. And so, and for error correction probability, we want to go much beyond 99.9 to reduce the overhead. And so 99.99 is very challenging target, I would say, but still, I don't want to say it's impossible. So, for example, if you think about 100 nanosecond long 2-qubit gate, the required, say, coherence time is basically milliseconds for 99.99 for as a rough estimation. And this is not really impossible number for our system. So hopefully, in some years, we can improve further our fidelities, gate fidelities toward that numbers. Okay, so there are other platforms are also making rapid progress. For example, recently neutral atoms become a strong competitors, and they are rapidly scaling up, and also fidelities are improving. Trapped ions, not yet, say, as much as scaled as neutral atoms, but fidelity is very high for trapped ions, and they are also making good progress this year. So we will see which one or all of them can reach our target. Okay. So for superconducting quantum computers, there are, as I said, the design of the superconducting qubit is a lot of freedom. So different groups have different designs, but roughly speaking, there are two directions. One is with tunable frequency qubits and tunable couplers, and the other is fixed frequency qubits and fixed coupling. So there are pros and cons on each approach, in each approach. So with tunabilities, we have a lot of freedom, and that allows fast gauge and suppressed residual coupling, and also tolerance for publication errors. But also it introduces a lot of complexity and high wiring cost and additional control, which may introduce additional decoherence. And on the other hand, with the fixed frequency qubit and fixed coupling, the circuit could be simple and low wiring cost, and no need of flux bias, and it tends to have long coherence. Of course, it has a limitation in the flexibility, so 2-qubit gate tends to be slower, and there's always some residual coupling between neighboring qubits, and it's vulnerable to process variation and two-level systems. So there are pros and cons, and these days many groups are looking at some combination of these. For example, IBM used to work on this side, but nowadays they are using fixed frequency qubit, but the tunable couplers, so like this. And there are groups working on bosonic code in high Q resonators instead of qubits, and that's another approach. So at weekend, we are also developing our superconducting quantum computers, and here we are still working on fixed frequency and fixed coupling, because we want to make the system as simple as possible. So here, this is a cartoon of our system with a 2D array of superconducting qubits on top of silicon substrate. The substrate has many superconducting through silicon vias to combine tightly the top and bottom ground planes of the chip, and to suppress unwanted crosstalk and spurious modes. And we decided to bring all the microwave signals in and out from the back side of the chip in the vertical direction to avoid any complicated wiring on the surface of the chip. So the microwaves are delivered through these coaxial cables through the package. And then on top of the chip, we also have a superconducting shield flip cover to suppress, again, unwanted coupling and unwanted modes. Okay, so these are chips we made. This is 16-qubit chip, 64-qubit chip, and here 2 centimeter by 2 centimeter and 8 centimeter by 8 centimeter, 8 by 8 qubits. So these are square lattice of 2D array fixed frequency transmons. And so this is a zoom up of one of the chip, and so basically this is a unit cell structure for our large scale chip. So containing 2 by 2 4 qubits, and so in this case the design is a concentric qubit transmon qubit between central pattern ring with a Josephson junction connecting them. And each qubit is coupled to readout resonator, and each resonator couples to the filter resonator, and then connected to the central port for the readout. And the neighboring qubits are capacitively coupled. And so these are zoom up of Josephson junctions, which is like a 200 nanometer by 200 nanometer aluminum tunnel junction. And yeah, but otherwise the structure is typically very deep, order of 100 microns. Okay, so this chip has a structure on the backside where, if you look at the cross section of the signal lines from the backside touches those parts for qubit control, which is capacitively coupled to the top surface qubit. And then the readout port is connected to the central beer and deliver the readout microwave tones. And that microwave signal goes into the resonator and then reflected back to the same port. Okay. So this chip is mounted on a specially designed package with many coaxial cables with spring contacts. And the chip is mounted and then with a cover chip, and then press them to the contacts to make the connection tight. So the microwave control and readout signal is delivered through these coaxial cables. And then this package is mounted in our Dyson refrigerator in the magnetic shield, and then cool down. Right. So for this 64 qubit system, we have in total 112 lines into the fridge and 80 lines into this package. So some lines are for pumping amplifiers. Okay. Right. So we are also developing now 144 qubit system. Again, our architecture is very scaling up because we can just copy and paste our unit cell to make a larger array and to make, for example, this is 144 qubit chip, 12 by 12, and just repetition of the same unit cells. So as I said, so this is our activities for the scaling up, but we are also focusing on the improvement of the fidelities. So here, this is our recent achievement on the improvement of the readout fidelities. So maybe you noticed that in this 16 qubit chip device, the unit cell design is a bit different from the previous one. The qubit is not concentric anymore, single island and connected to the ground with a single Josephson junction. And the readout resonators are also different design than before. So here we demonstrated four-fold multiplex, frequency multiplex simultaneous readout by sending 4 different tones into the central port, and then those tones are delivered to each resonator with different frequency, and then picked up the information from the qubit and then reflected back to the same port. So, right. So we designed this filter resonator properly such that we allow very strong coupling of the resonator to the environment. So that means a very fast response. On the other hand, we protect our qubit from the energy relaxation very effectively by using this filter properties of this specially designed filter circuit. Okay, so, and using this device, we achieved the qubit readout, single shot readout within like a 6 nanosecond pulse, 4 qubits simultaneously with different frequencies, and then obtain the readout fidelity beyond 99.9% in is 1 qubit, but in average is 99.7% or so. So compared to recent progress in this field, in terms of the readout time and the readout error, our data is here, like 60 nanosecond and 3.9, better than 3.9 fidelity. And there are, of course, many other groups working in this direction, and more recent data are here, and even better fidelity, but a bit longer readout time. So I believe our field will make more progress towards better readout and a bit faster readout and better fidelity. This is important for quantum error correction with mid-circuit measurement. Okay, and also we have to check that this readout does not induce any leakage to the upper excited state or additional readout induced back action error. So our postdoc did a readout, repetitive readout in every 100 nanosecond up to 750 times, and then check how the population of the G state and E state and even F state, upper excited state, to check if there's any leakage to upper states. And that turns out to be very small for this readout. On the other hand, measurement-induced decay causes some additional infidelity, and that part we have to improve further. Okay. And this is another topic. So this is for the improvement of the 2-qubit gate. So as I said, in our large-scale circuit so far, we use fixed frequency qubits and fixed capacitive coupling, and which tends to give a longer, slower 2-qubit cross-resonance gate, about 200 nanoseconds, 300 nanoseconds. So the fidelity we have so far is about 99.3%, not yet 3.9 fidelity. So we are trying other approaches, not yet in a large-scale circuit, but in a 2-qubit experiment. So here we developed the so-called double transmon coupler, which means between two data transmon qubits, we add two more transmons, which are connected via squid loop. So this works as a coupler. So here, and this looks a bit complicated, but in the end, these two coupler transmons creates symmetric and asymmetric coupled modes to mediate the interaction between the data qubits. So like this, so between data qubits, there are asymmetric and symmetric modes in this coupler. And because of the symmetry, they give different opposite signs of the coupling constant. And also the coupling strength is tuned by the tuning, tuned by the flux bias of this squid loop. So that's how we compensate each other to suppress the coupling, switch off the coupling, and also induce coupling. So this was done by our postdoc Louis Lee, and then based on the proposal by Hayato Goto. And so here, okay, this is for energy eigenstates of this system. These two lowest from this data qubit, and then upper state is this coupler modes, and which is strongly depending on the magnetic flux bias to the squid loop. And when we are at the idle bias point, where the qubit residual coupling is very much suppressed down to kilohertz level. On the other hand, when we apply magnetic flux bias at some point, we can induce very strong interaction between qubits, so up to 80 megahertz. So there's a on-off ratio of more than 10,000 of the ZZ interaction between the data qubits. And if we apply magnetic flux pulse in the time domain like this, for example, we have an excursion of the Kapra mode down to here and up, so which induces a lot of phase shift of the qubit states because of the hybridization, and then induce strong ZZ interaction. So this gives a fast control Z gate between the qubits. So by the way, when we switch off the coupling, the single qubit gate shows a very high fidelity, nearly 4.9, because of the high coherence time of this device is like a few hundred microseconds. And then, so then we tried our 2-qubit gate, and that gave us more than 3.9 gauge fidelity within 48 nanosecond gate pulse. And also we found that the leakage to the upper states is extremely small. Okay, so this is an example of a 2-qubit high fidelity 2-qubit gate, not yet integrated in a large system, but we are considering about that. And yeah, one extension of this work is to add additional capacity here and to modify the energy level diagram to make it a bit more flatter in this zero flux bias region, the suppression of the ZZ coupling, and then in principle we can avoid any static DC bias and by allowing a small offset bias here, and but we can still implement high fidelity 2-qubit gate. Okay, yet another approach for 2-qubit gate, high fidelity 2-qubit gate. So here again we want to avoid any complicated DC bias line. So here we implemented all microwave 2-qubit gate by using another transmon qubit in between two data transmon qubit. But this is all fixed frequency transmon, so no DC bias and only controlled by microwaves. And so here in this 3-qubit system, including Kapra, we use this is basically the energy levels of this 3-qubit system, but we use this transitions, including the upper states of the Kapra, and so these two transitions are actually influenced by the state of the other qubit. So this gives a conditional state transitions, and gives the kind of dispersive shift between these two states, initially degenerate if there's no other qubit. So by using this dispersive shift, this driven transition gives draws a different trajectory on the Bloch sphere depending on the state of the other qubit. So that gives a geometric phase for the conditional phase gate, and by using this effect, we actually implemented a high fidelity 2-qubit gate in this device. And so this is not yet 3.9 fidelity, but almost, and within like 150 nanoseconds. And also this circuit decoupled the 2 qubits when it's not driven. And so we are also considering this for a larger scale implementation. Okay, so this is an additional topic. This is the development of the Josephson parametric amplifiers for broadband and low noise amplification of microwave signals, basically for better readout of the qubit. So this is not qubit, but this is still using Josephson junction nonlinearity for microwave devices. So here we have one-dimensional array of Josephson junctions, 2,400 junctions in series as a waveguide. This is spiral waveguide from input to output. And because of this nonlinearity given by Josephson junction, we use this for parametric amplification, basically four-wave mixing parametric amplification when we apply strong pump power along this waveguide, the signal microwave is parametrically amplified. So actually, so there has been this kind of Josephson junction traveling waveguide, traveling wave parametric amplifiers since 2015 from the first demonstration by MIT group. The issue was the relatively large insertion loss or internal loss of the waveguide because they were using dielectric capacitance for the impedance matching. So here we design our circuit such that we use only aluminum planar process, no dielectric layers. So using this stub capacitors and air bridges. So we minimize the internal loss. So as you see here, when we do not apply any pump, the transmission of microwave from 4 to 12 gigahertz gives at most 0.5 dB loss in the whole range. This part is the band gap because of the periodic modulation of this waveguide. So here we actually, when we pump the input the pump power, we see the high gain of the signal microwave up above 20 dB in a wide bandwidth of a few gigahertz at least. And so we also check the added noise in this amplification. So in the standard quantum limit, there's a limit of 0.5 added photon in this amplification process. But this device, because of the thanks to this low internal loss, the added noise is nearly the quantum limited, about 0.68 photons in the high gain regime. So this turns out to be very good parametric amplifiers for amplifying small microwave signal. So that's the end of my story. And so this is our prospects. So we are now fighting against the inhomogeneity of the junctions in our device. And also we are trying to improve the coherence, hoping for like a few hundred microseconds and to achieve say 3.9 fidelities in the whole chip. And we are scaling up to 144 qubit system and hoping for demonstration of some error corrections. But we know that even though it's scalable in a small scale, cannot be scaled up to millions of qubits. So for that, we need some additional ideas for how to make it multi-chip or multi-modules. And so that's what we have to work on from now on. Okay. And so as a summary, actually, our field started from interest in superconductivity, and then people started to look at macroscopic quantum coherence in a macroscopic system. And then the superconducting qubits and circuit QED were developed. And nowadays we are building quantum computers. So actually, yeah, we started from condensed matter physics and then learned atomic physics and quantum optics. And now we're making large array of artificial atoms and creating kind of meta condensed matter physics in a large array of Josephson qubits, superconducting qubits. So that's a kind of history of our field. Okay, but of course, to do something interesting, we have to achieve fidelity and larger scale, and that probably requires quantum error correction, and that's our challenge for future. Okay, so that's all, and yeah, so that's our team at Weekend, and thank you for your attention. Mm. Mhm. Mhm. Okay, so 5 years from now. All right. So you said number of qubits or a number of physical qubits? Okay, right. It's hard to predict, but if you believe a roadmap from big companies, we have to reach a million qubits. But I think it has to be very challenging in 5 years. But still, I wouldn't say it's impossible, but challenging. And yeah, I think as a field, we still need some uh, kind of breakthrough ideas for scaling. Very, uh, currently the main limitation is okay, qubit chips are okay to scale up, but I think wiring is a very stringent limitation for the moment. So we have to find how to uh, wire all of them in a scalable manner. So people are looking at, for example, cryogenic electronics, and that may be a solution, but it's not so straightforward either. Yeah. Mhm. And you ask more? Yeah. Mm, 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 mm. Okay, so slowest gate is usually 2-qubit gates, and so our target is something like below 100 nanoseconds or hopefully 50 nanoseconds. Uh, and the fidelity, as I said, I think currently our community is aiming at like a 3.9, but for next 5 years, people definitely interested in achieving 4.9. Yeah, that's very challenging. So
Yeah, thank you for the talk. There was one slide where you present the fidelities on the x-axis, and then you say the required coherence time for operating a 2-qubit gate, 100 nanosecond 2-qubit gate.
Right.
So how do you estimate those coherence? How do you estimate the coherence time there?
Okay. So yeah.
Yes, this one. Yes.
Okay, so here, right? Okay, just a very rough estimation. So, so if we assume we actually implement 2-qubit gate with 100 nanosecond time. So basically, if we consider the coherence limit of this gate, if the coherence time is 100 microsecond, then if the gate time is 100 nanosecond, the ratio is 1,000. So that, roughly speaking, that allows 3.9 days. If the coherence time is 1 millisecond and the gate time is 100 nanosecond, that roughly gives 4.9. Of course, there are a lot of details. Right. So yeah, this basically gives the error rate. Yeah. And so how much error happens within 100 nanoseconds given this error rate.
Okay, thank you.
Right. So surface code is very generous for us, and requiring only nearest neighbor gate. Yeah, but of course, yeah, people looking at the say, more efficient quantum error correction code like a QLPC code, but that requires much more for experimentalists. So for example, IBM proposed this BB codes, and they are currently. I heard that they are currently implemented experimentally six-fold or seven-fold connectivity that cannot be on a planar device. So they add some additional layer to connect more qubits each other, and that's quite challenging, demanding. Yes, yes. Yeah, that was, yeah, retrospectively, that was very challenging, very difficult experiment compared to the recent ones. So, because the coherence time was at most nanosecond, we have to operate our qubit within few hundred picoseconds. And uh, the way we did the manipulation was so as I said, that's a two-level system: Cooper pair box, zero charge, zero Cooper pair state, and one Cooper pair state. So we initially prepare zero state by shifting one state up, and then by applying the very fast gate voltage pulse, we bring it down suddenly, non-adiabatically, and let them start to oscillate, and then switch off the bias pulse, and then the population is kind of frozen, and then we measure. So this voltage pulse has to be very fast. So we use that at that time the state-of-art pulse generator for telecommunication. At that time, it was 12.5 gigahertz pulse pattern generator, which creates from 80 picosecond pulse to longer. So by changing this pulse time continuously, we studied how the final state population oscillate. So that's how we. Right. Yes. Yes. So now the experiment is much easier.
Okay, so I have a question which it's about superconducting qubits, but it's not something that you talked about. So this has been something that I've been thinking about for the past 1.5 or 2 years. So we've been doing quantum computing using digital quantum computers. I mean, starting with your quantum computer first, with we used when Akhil had you the measurements, and then we've been doing similar calculations using the D-wave quantum annealer. That's also superconducting qubits. The results that we get from the quantum annealer is always much more accurate. And is it only because of the fact that quantum annealers do not use gates, or could there be some other reason for that?
See, think so. Yeah, I think this accuracy strongly depends on the particular error rate of the particular device, and yes. Yeah, for example, if our gate model qubits have better fidelity, maybe the error rate is lower. And so I cannot directly compare them, but yeah, of course, with quantum annealer, you always stay at the ground state. So for them, the coherence is not a big issue. But for them, what matters is when they go across the minimum energy gap point, error can happen if the adiabaticity is not well preserved. So yeah, it may depend on the problems, I would say.
But we've done the computations for at least 3 different properties, like the ground state energy, dipole moments of molecules,
Right.
and more recently hyperfine structure constants.
But yeah, those properties are all encoded and kind of embedded in the problem of the I would say in quantum annealing, you kind of model it in some Hamiltonian sweep the parameter, right?
Yeah.
So I think this, and then also for gate model, you use VQE, right? Yeah.
Or some other algorithm.
So yeah, I don't have a good answer, but I believe that those accuracy depends on the problems and
or do you think the gate, the fact that annealers don't use gates, could that be the main reason?
Main reason
for the accuracy in annealing?
I think, say, in that kind of NISQ applications, the gate error matters a lot.
Oh yeah.
But for say quantum error error correction, that's not the case.
Yeah. That of course we haven't done. So
yeah.
Thank you.
Yeah, like tens of nanoseconds or at most 100 nanoseconds. Yeah, because they stay at the ground state in the annealing process, so the coherence that doesn't matter so much.
Okay, thank you.
Yeah.
Interfreeze communication. Do you still use microwave, or do you do the transduction to optical?
Yeah, that's a big question. So first of all, if we can do everything within one fridge, that would be much easier. So, and even for multiple fridges, instead of building multiple separated fridges, if they can connect them physically to build a kind of one gigantic fridge, that would be easier because we don't have to bring our microwave signal into outside the cryogenic, right? So, but if you really want to use multiple fridges physically separated, yeah, we definitely need to do some optical transduction, and that's another big challenge. Yeah.
It's been tried anywhere, that's optical transduction?
Oh yeah, people are trying. Yeah, but not yet high fidelity and high efficiency. So yeah, this microwave to optical transduction is very interesting but challenging problem.
Is there any more question? Last call. If there is no more, let's thank the speaker once again.
The next program. Have copy or yes, yes. You're up to you. You decide.